So welcome to session 3, uh, applying Julia to real-world physics problems. And in this session, we'll consider two very simple physics problems. The one-dimensional discrete system, which is known as logistic map, which was derived from the insect population models. And the other thing that we are discussing is the Lorentz attractor. Now, these are two very iconic systems where the logistic map represents the discrete system and the Lorentz attractor represents the continuous system. So let us start where we left off. Now, basically, our basic assumption is most physics problems boil down to solving a differential equation. While it is easier to code the algorithm While it is easy enough to code the algorithm, with Julia life can be easier. Now, this will be especially clear if you are doing the logistic map example that I'm providing, that I have started the net from. Why? Because I'm going to use the dynamic systems package pre-built in systems. So famous systems like the logistic map is already pre-built in. So for the logistic map, I will do it pre-built in. For the Lorentz system, I'll do a bit more coding. So these are the two systems we are considering. And let me just stop sharing the slides and go to our Julia code. So I have precompiled the code. I have precompiled the code. Uh, yeah, and here what I have done, I'll just show you. So the first things I've done is I have initialized dynamic systems and Python plotting. Then I have initialized this logistic map system with the parameter r equal to 4. This I is my index pointer. This I use for starting my calculations. This p values is a set of parameter values which I vary from, which is r in the case of the logistic map, which I vary from 3 to 4 in steps of 0.001. This is the initialization of random initial conditions. So I'm using the rand function and I'm using this for loop to do this rand function 10 times. So I'm getting 10 initial conditions which are random. Yeah. This n is 2000 points and this t transient is 2000 points. What do these certify? So t transient means allow 2000 iterations to happen, and these 2000 iterations we will ignore and we'll call them transient points, meaning that's not the long-term steady state behavior of the system, because we are trying to draw the bifurcation diagram of the logistic map in which we have to show the long-term steady state behavior. And this n is the 2000 points of iteration we do after we reach a steady state. This can be a smaller number, but just for the sake of symmetry, I have kept them same. Now, there is a function called as orbit diagram, in which if I give the differential system, the starting index, the indices of the parameter and the parameter values, given the starting initial conditions and the number of points to be iterated and the number of points to be considered as transients, it will generate an array of data. So see, for before period bifurcation, what was your final steady state value is 0.6, but after a point when period bifurcation is reached, You see, now it is not a single value. Now it is multiple values. For each point, it is a multiple value. L is the length of parameter values. Now, parameter values we have said as this. So, how many parameters are we considering? So, from 3 to 4 to 0.001, so we'll be considering 1001 parameters. And right enough, 1001 parameters. X is we are going to have a vector which is going to be consists of that many spaces as n into L. The number of points to be taken into the length of the parameter value, and same we do for y. So the copy command is very nifty. Now we run a small for loop for j is equal to 1 to L. So 1 to 1001 x of 1 plus j minus 1 into n to j into n is p values j. Now let's take p value 1, right? J value 1. So what does this turn out to be? 1 plus 0, so 1 to 1 into 2000. So x1 to x2000 is equal to p values j, and y1 to y2000 is equal to output 1. P values 1, output 1. So on and so forth. So we want to now finally plot it, and plot it we shall. So this code generates my plot, which I will show you momentarily. Now my plots are not this is the kernel, it is not an IDE, so it does not have what you say as inbuilt plotting space workspaces, etc., etc. So it shows the plot as a pop-up, and this is the pop-up. So you can clearly see the bifurcation diagram, logistic map, right? From parameter value 3 when period doubling starts, and slowly we go to the point at parameter value 4 where we have full-blown chaos. So we have we have chaos even before parameter 4, but here there's no evidence of period doubling, as we can see. So now it was period 1 before this, so it become period 2, then it has become period 4, then period 8, then this gap is period 16, then this gap is period 32, period 64. So with a simple implementation, without using any coding, using built-in packages, we can generate this diagram quite easily. But for the logistic map, as I've already said, I'm going to do a bit of coding. So bear with me. It will get a little bit slow in that portion of the thing. So once again, I display my Julia tab, and now for because I'm not using dynamical systems, I will need something else, and the something else that I'll need is ODE. I'm already using PyPlot, so Python plot, so I don't need to use Python plot once more. I just need to use ODE. It's a fairly easy to initiate system, and let's have a look at what we're going to do. First things first, we are going to define the differential equation. So this will define the differential equation, this function, and it will return the derivatives. So this will return x dot, y dot, and z dot. This function, like, next I will define the time interval I want this simulation to run, and initial positions. So this is the time interval, and this is my initial position in space. X is 0.100. Now, if you are so inclined, it is a simple matter of making this 0.1, right? And if you are so inclined, I can make, if I want to make this run even faster, I can put dt is 0.1, df as 100, and I can collect this. So now it becomes a 1,000 element array. So there'll be 1,000 positions to calculate. So the next part is the hard part to implement, always the plotting. So how do we implement the plotting and the solution? So first we start with the solution, and the solution we have defined as follows. These are the constants sigma, rho, and beta. Where are these constants used? In this equation, in x dot, y dot, and z dot. And then what I have done, I've used an ordinary differential equation solver to give me at respective time what is the position, given that the function f contains the differential equations, r naught is the initial position, and t is the time variable. So, and what I will do is I'll map the solution in positions of the first vector of position, the first component of position I'll map to x, the second to y, and the third obviously to z. That's all I'm doing here. Now all that remains is plotting this. Now this is going to get a little bit more involved because it's a 3D plot, and these can be quite uh, time consuming, but ours has run quite fast. So I'll just show you our 3D plot. This is my 3D plot. Yeah, it's quite an interactive 3D plot. I can turn it, and you can see that there is the double score attractor that we see in Lorentz map. And this is I have done from using the simplest ODE solver. I have not used the complicated differential equation package. So you can see, you should one should appreciate that this is quite uh, uh, not an achievement, but it is quite on a priori basis you've done it. You're not using a dynamical system package to spoon feed you everything. With this, my physics problems exploration into Julia are done. Now I've shown you what to do, how to do it, and the next thing I would like to do is to know is what not to do. So the first mistake I made, I overestimated my computer. Now this is a laptop. I generally run these simulations on my desktop PC, and rule of thumb is desktop PC will at any given time be 3 to 4 times faster than a laptop. So this is the first thing I did wrong. So is there any way I could have made it faster? Yes, by taking a smaller data set and adjusting it for here. But this is what you need to understand: your limitations of your computer. If you have a very limited computing capacity, you cannot expect to run the full scale version of uh, your physics code. Then the next thing not to do, trust your generated data implicitly. So we have not we have not seen this as of yet, but when you run simulations, sometimes you can generate spurious data because of truncation errors. And at that point, you have to ask yourself, how do I know that my data that I've generated is genuine or is spurious? Now, there are several ways of doing it. Doing verification runs, taking larger statistics or larger amount of data points, you can verify and you can get an idea. Okay, this data is good, this data is not good. Okay. And the third thing I would advise you to do, uh, advise you to do, not to do, when you're coding with Julia, is be abreast of the latest codes as Julia changes quite rapidly, right? So, as I've already mentioned, several coding habits that I used to in version zero point 0.5 are no longer available in version 1.5. So, what one does in such cases? Remember, humanity is not one person. We can always go to the fora and be vocal about your problems. Somebody or the other will address you. It is a large community of enthusiasts who are dedicated to applying Julia in various fields. So you may never know that what perspectives you will get in the forums. And these are a few of the references. So for base Julia language and SymPy and plotting libraries helps. I have used code examples and code from here. This is the Julia cheat sheet. So if somebody is interested in learning Julia from startup, what I would expect you to do is open Julia, open this web page, and open the Julia cheat sheet as well, and start experimenting with it. This was the website that helped me with SymPy immensely because, as you know, SymPy is slightly uh, rare thing that people use Julia for. Most people use Julia for its fast computation. When people want to do symbolic math, they stick to Mathematica. But I've shown you it can be done with Julia. So the double pendulum code was to be also displayed, but the double pendulum code is have which the animation I was showing you a time stop image of its animation I was showing you a timestamp image has certain dependencies that do not work well on my current computer. So I'll be working on updating it. And if you want to get a general idea of computational physics, this is the website where you start from. Now, acknowledgements. Of course, I will acknowledge my institution, which is organizing this event, my department, and my colleagues who asked me to step up and present this. I would like to thank a few more people. my entire family for giving me an undisturbed environment to make these videos and always encouraging me when I made a blooper and I had to reshoot videos time and time and time again. I would thank all of you for being such a wonderful audience, and I will leave you. In conclusion, I will say one, if one cannot solve the problem easily, then it is not that their approach is wrong always. It can also be that you are using the wrong tool, and more often than not, the right tool may be Julia. And thank you all for listening in. If you, I have a small questionnaire prepared for you that will also be given on to you. And if you have any uh, doubts or queries, even on YouTube, you can look at the Julia Cloud uh, or the Julia Computing channel, and they will give you all the necessary tutorials and demos. So I'll leave you with this statement.